How's everybody doing? Welcome back to Math for Healthcare video lecture series. We're going to continue on with conditional probability, and one of the things that come out with that is certain events we call independent events. So let's see what we're talking about. So independent events is they're a special case where the knowledge about the occurrence of one event does not affect the probability of another event. So as a non-example, we saw that whether or not the first card drawn from a well-shuffled deck of 52 playing cards greatly affects the chance of the second card being drawn, the deck being a face card. These events, first card drawn as a face, second card drawn as a face card, are not independent from each other. I think that we might as well, let's take the time and do the tree diagram for this of conditional probabilities. Before we move on to examples of. All right. First of all, I'm going to call my events first card drawn a face. I'm going to call that H1. Or sorry, let's say that's let's do the example we have here. Let's say we'll call it F1. First card drawn is a face card. And we'll call F2 second card drawn is a face. Okay? So, what do we got here? We have a tree diagram, right? And maybe try and draw this on your own. Hit pause and see if you could fill this all out. Oops, we're going to use F2, F2 complement, F2, and F2 complement. All right. Now, what goes in these? Here we have. Try and fill this out on your own, but this is probability F1. That is face cards. Let's see, what do we got? We got 12 face cards, 52 cards. So that's our probability of a face card being drawn first. Probability of a face card drawn second is 40 out of 52. Now let's recall is what goes in this next layer. These are over here. We have conditional probabilities. I'll do those in red. So for instance, this red edge, what do I mean by that? That is because I'm already out here at F1, so I know that happened. So I'm looking for the probability that F2, or a face card gets picked second, given that a face card was chosen first. And that is, well, it was since the face card was chosen first, we have 11 face cards, and there's 51 cards left. Sorry about that. Thank you for... This is, so we got 11. There's 51 cards left. All right, that gives us 40 out of 51 for the probability that the second card is not a face card, given that the first card drawn is a face card. All right. And similarly down here we fill in. Now here the first card is not drawn a face card, so in this over here, right, we're looking at the probability that the second card is a face card, given the first card was not a face card, and that is... Now we still have, since it wasn't a face card, we got 12 face cards left, and we have 51 cards left. Similarly, and that's going to leave us with 39, 51 for the probability that the face card is not drawn second, given that a face card was drawn first. So that's a whole tree diagram. And notice that why is this non-example? It's a non-example since, a non-example of not as here it does affect it. How do we know that getting a face card or not affects the second card? It's because the probability that we get a face card second, given that we got a face card first, is not equal to the probability that we get a face card second, which, by the way, is going to be 12 out of 52. This face card second. But, so they're not the same. So that should tell us, what are we looking at? Independent events are going to be events where that equality holds. In other words, the first event happening here, face card first, doesn't affect it. So let's see. Can you think of an example like that? That's right, coins. Any coins. We could think about that as flipping coins. We could draw the same tree diagram. All right. Except for now, say we get a... Oh. A heads first or tails first. Notice tails is a complement of that. And then second, we get a head second or a tail second. We could get a head second or a tail second. Now, I should say, sometimes people don't put in the 1 and the 2s there. Well, and that's okay, because generally speaking, this second action is the second time happening. But it could get a little troublesome with some other notation. So I like to leave that H2 and H1 there instead of just H and H. All right, now here, certainly the probability of getting a heads is 1/2. Fair coin, of course, 1/2 for tails. Now notice here, let's see where I have this star, right? That star is going to be the probability of a heads second, since I'm already at heads 1, given a heads first. Now, notice, what is this equal to? This is just equal to 1/2, or the probability that we get a head second. And so this is an example. We'd say tossing 2 coins, they're independent events. All right? Because it changes. So here, it does not change. Apologize about that misspeak. And that conditional. And that's our definition. Events A and B are independent if and only if the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. Now that's our definition. If we're asked to test whether 2 events are independent, we want to use the product rule. And remember that for conditional probabilities, we saw before that the probability of A intersect B equals the probability of A times the probability of B given A. Okay. All right. That's well and good. Remember, what do I think of this as? That's multiplying down some path of my tree diagram, right? It may look something like this, that red path down the tree diagram. All right, well, if A and B are independent events, we have, this must be times the probability of A times, probability of B given A is equal to the probability of B if A and B are independent. So then we could use our new product rule, and this is the best way to test for independence. All right, you can't just think about it and guess whether things are independent. You will be told sometimes things are independent, but in general, we're just not sure. And this is the best way to be able to check if two events are independent. The product rule. Probability. Does the probability of A intersect B equal the probability of A times the probability of B? All right, so let's look at an example here. Let A be the event that a randomly chosen employee has a college degree. Let B be the event that a randomly chosen employee's income is more than $60,000. Are A and B independent events? All right. Well, for our test we saw we needed a few things. We needed remember our test. Let me write that up here. Test is, does the probability of the intersection of two events equal the probability of A times the probability of B? Okay. All right, so here, probability of A intersect B we're going to need, probability of A we're going to need, and the probability of B we're going to need. Go ahead and take a minute and find that on your own. Maybe hit pause. Okay. All right. So the intersection, that's the probability that a randomly chosen employee has a college degree and the employee's income is more than $60,000 a year. All right. So there's 720. Intersection is 720 divided by, how many total students do we have here? Should have done that beforehand. Hopefully you got it. And there we go. That's what I need. Looks like we got a total of 4,000. So this is 720 over 4,000. Probability of A is, let's see, the randomly chosen has a college degree. That's looks like 720 plus 400 have a college degree, which gives me 1120. And I still have the same sample space, 4,000. And the probability of B equals, let's see here, making more than 60,000, that's going to be 840 plus 720, what was that, 1580, no, 1560, sorry, 1560 out of 4. All right, so we got to test those probabilities. It's probably easiest to just get these into decimal. And then we check. Okay, our test is 0.28 times 0.39 equals 0.1092, not equal to 0.18. All right, so we would say that these events are not. No, they are not independent. I know, and it changes. The probability changes, and we just used a test for that. If you wanted to, you could try and find the probability of B given A separately, and you'll see that you find that same thing, that it does change. It's not the same as the probability of B. All right. How about this? We got experiments. Probability of A is 0.2. Probability of B is 0.6. And the probability of the intersection is 0.13. Are the events A and B independent events? Well, let's see here. 0.2 times 0.6 is 0.12. So, no. Because of this reason. Notice that you have to supply. This is why they're not independent. All right, let E and F be events of experiment. Probability of E is 0.5. Probability of F is 0.5. What is the probability of E intersect F? Well, here, if they were independent events, the probability would be 0.25. However, we don't know because we don't know whether they are independent events. And you'll see this if you look at any sort of statistical stuff. They will say that certain events are independent or assumed independent, all kinds of things like that. All right. Let's see. Let's look at a couple further problems. Let A and B be independent events. Probability of A equals 0.4. The probability of 0.6. Find. Well, we can find their intersection. I'll do that one. We can find their intersection. That's going to be, because they're independent, we could find the intersection by multiplying 0.4 times 0.6. And that's going to give me 0.24. Okay. And then from there, we could find the union with our union rule. I'll let you do that on your own. Oh, how about the probability of A given B? Oh, they're independent, so that just equals the probability of A. Remember, we're using this independence quite a bit, and that's equal to 0.4. Let's look at this third one. 8 black balls, 4 white balls, and 6 red balls are placed in an urn. 2 balls are drawn in succession. What is the probability that the second ball drawn is a white ball if the second ball is drawn without replacing the first? All right. So there, we really need our Venn diagram to think about it. Okay. Notice we're only talking about the white balls. So we could really just make it 2 categories here. We could say, all right, let's let W be, W1, first ball is white, and W2, second ball is white. All right, so what do we have here? We got white 1 or not white 1. White 2, or the second one is not white. White 2, or the second one is not white. And you should be able to fill out this on your own, this whole tree diagram. Let's see how many we got. 4 white balls, so it's going to be, the first one is 4 out of, how many total balls we got here? 10, 18. And so that means that we got 14 out of 18 is a non-white ball. Now, how about, now we have conditional probabilities, and we see what's the probability that the second ball is white given that the first ball is white. It's up here, right? That's going to be, well, now we only have 3 white balls left and 17 total balls. So down here it's 4/17. And then the white, now here, right, what do we got? What's the probability of white second given that the first ball was not a white? So we still have 4 white balls, but only 17 total balls left. And then we have 13 and 17 here. Now, but notice, so this is an example where it's not independent events, right? Getting a white ball second. A big sign that it's not independent is drawn without replacing the first, just like in our card example. Those are generally going to not be independent events. All right. So here, what's the probability of a white ball drawn second? Let's think about that. That can either be Well, what? You could either get a white ball first and a white ball second, or you could get a non-white ball first and then a white ball second. Notice we don't have to worry about subtracting out the intersection from that union, because that's really what I did. The union is because each intersection, so this one in red is this path, right? That's an event because I'm taking the intersection of two events. And then the yellow path is this guy, and that's an event itself. That whole path, the intersection, is and those intersections, the yellow and the red, they are mutually exclusive here, so we don't have to subtract the intersection. We could just add these. And who remembers? Oh yeah, we remember we multiplied down the path. So this is going to be 4/18 times 3/17 plus 14/18 times 4/17. Those are all our paths to W2. Right, these guys here, all our paths there. So when we multiply those, right? Well, I'll let you do that on your own, but what we end up with is 4/18. And I'll let you think about why that comes out that as well. But we do need to know how to get to find those intersections and probabilities. Okay. Now let's see. In a particular pain clinic, 10% of patients are prescribed narcotic painkillers. Overall, 5% of the clinic's patients are addicted to narcotics, including painkillers and illegal substances. Out of all the people prescribed pain pills, 8%, sorry about that, 8% are addicts. If a patient is an addict, what is the probability that they will be prescribed pain pills? So let's think about this. 10% of patients are prescribed narcotic pain. Here we have to be, we're going to use a tree diagram, I'll give you that hint, but we got to be careful, all right? What are our two events that are happening? Now we have, let's say, P is prescribed painkillers. No. So that's P, not P. And how did I know to do that? Because I was given that I know what percent, I know the probability of P. Okay? And this has got to be 0.9. Now, what's my second set? We'll call it A. That person is an addict. I don't know what that really, how they define that, but 8% are. Now let's think about that. We know, what is this saying? Out of all the people prescribed pain pills, okay, so A is over here. Addict, not addict, addict, not addict, not addict. Now, remember, what's this? What do we got to put in here? That's the probability of A given P. In other words, what's the probability a person is an addict if they were prescribed pain pills? Another way of saying that, see, this is where it's tricky to find that. Out of all the people prescribed painkillers, so that means picture walking all the way to P, because I know that you're prescribed a pain pill. 8%, so 0.08 addict, and this is 0.92. Now, notice, I don't think we're given this or this, okay? So if a patient is an addict, what is the probability that they will be prescribed pain pills? All right, let's think about that. We're looking for now, notice 0.08. Let's write some things down. So 0.08 tells me that was, it's the probability, I'm going to use probability because I have this P going on, of person being an addict given that they were prescribed pain pills. Now, that was my 0.08. What we want to know is what we're being asked to find is the probability of being prescribed painkillers given that you're an addict. Now, we're not quite ready for this. And here, this is, to calculate this, we need Bayes' theorem, which will be covered in the next video. All right, please let me know if you have any questions, and have a great day.